Chapter 18, slides 10 through 17. Okay, we've just gone over how to put a group onto a benzene ring. And I want you to first focus on the fact that whatever that group might have been, bromine, carbon, it was this first step that was rate determining, right? So although there is another step to reform the aromatic ring, this step arguably is the hardest. Just want to remind you of the starting point and the intermediate. This is what's going to play a role in a lot of the discussion for this next section of slides. Okay, the product over here. Now, what we're going to be focusing on is just this first part, okay? The formation of the intermediate. This is going to frame the discussion that's going to lead to understanding how to predict the products for more complex reactions. So let's discuss the main two topics for this section of slides. We're going to look at rate effects, how fast the reaction can go, how efficient it is, and directing effects. Now, I'll go back to this again. We started with a clean, no substitutions off of the benzene ring as our starting material, and we're putting group number 1, the first group, onto our benzene ring, E. What I'd like to talk about is what the effects are when you already have a group on the benzene ring in your starting material. So let's say we wanted to put a second group onto the ring. If I started with this aniline species, basically an amine, right? Here's an amine. It's already a substituent on my starting material, and I want to brominate it. Or in the second example, I start with a ketone off of my benzene ring, and I want to brominate it. One of these benzene rings is going to react faster than the other. How can we figure that out? Well, that's why I drew this starting point to recall from the previous set of slides. How is the aromatic ring behaving? Understand that in both of the examples I gave you, you're using bromine, right? You're doing a bromination. So the key is not in the electrophile that you're putting on. The key is in the benzene ring because it differs due to the substituents it has off of it. Okay, think about how we defined what was happening here. This is another reason why I like to call it a pi nucleophile. Let's focus on that. The pi bond is our nucleophile. The better your nucleophile, the better the rate. The better the nucleophile is, the stronger the nucleophile, the faster the reaction. Okay, an improved rate. How do we make a nucleophile better? We need more electron density. Okay, we want to add electron density to the benzene ring. How do we add more electron density to the ring to make it a beefier nucleophile, a better nucleophile? Well, you do that by adding electron donating groups. So we're going to go back to that beautiful lesson I taught you in like the first few weeks of Orgo 1, how to distinguish an electron donating group from an electron withdrawing group. You do that through dipoles. You can also do it by looking at the atom directly off of the ring. If the atom directly off of the ring has a lone pair, which the nitrogen in this case does, it can very efficiently and effectively donate those electrons in and towards the benzene ring. You could also draw a dipole and say the hydrogens from the hydrogens out to the nitrogen and towards the ring. This is, either way you look at it, by induction or resonance, an electron donating group. In the second example, we have a carbonyl directly off of the benzene ring. So you look at the carbon. The carbon does not have a lone pair. Does that make it automatically not an electron donating group? No, we should look at the dipole as well. The dipole is definitely going away from the benzene ring. This is most definitely an electron withdrawing group. So if I want to make the benzene ring a better nucleophile, which is the better nucleophile? Well, the one with the electron donating group is. That's the one that's richer in electron density and more likely to react, right? As you can almost see by resonance, the electrons can come down and ultimately attack the electrophile, okay? So the donating groups help. So if I were to ask you which of the two would brominate faster, it's not about the electrophile, it's about the nucleophile. Who's the better nucleophile? Notice that I don't even have to predict the products. I don't need to predict the products because to answer this question, I'm looking purely at the rate determining step. I'm rate-wise, the first step is rate determining, so I don't even need to know what the products are to answer the question. I don't even need to really give you the electrophile. I could have just given you E plus and asked you the question. As long as the E plus is the same, I can compare. So what you see down below here is that the word activators just means something that's going to increase the rate of the reaction. Activators, groups that increase electron density on the aromatic ring, make the ring more nucleophilic, thus make them stronger nucleophiles, thus make them better for pi nucleophilic attack. So activators are effectively electron donating groups. Okay, so long and short, electron donating groups. Deactivators decrease the electron density on the aromatic ring, making them less electron rich, less nucleophilic, weaker nucleophiles. These are electron withdrawing groups. So if you can distinguish whether a group is donating or withdrawing, you have the power to determine the rate effects for different reactions. Okay, now I will show you the products for these reactions, and you'll notice that the groups placed on the bromines relative to the groups that we started with, the NH2 and the ketone, they ended up in different places. Now that's a whole nother story. We don't need to look at the products to determine rate effects, but how do we determine what the products are? We now have to start a discussion on directing group effects. Let's take that amine as the substituent already on the ring. Okay, so we have this amine. We've determined already that it is a strong electron donating group. So it's going to make this reaction go pretty quickly. It's an activator. Okay, I also want to remind you that you've been doing this all along. Remember when we were doing the Diels-Alder reactions and we had our Pac-Man right here? And you could have groups off of your diene. And you had to determine whether it was donating, withdrawing. And you could say that the OH in this position, because it has electrons that can donate in, or you could just simply look at the dipole, is an electron donating group. You could look at the carbonyl on the dienophile and say, yep, this is a withdrawing group. So really, I'm just going to do something kind of crazy here. What if I just connected these? This is not a Diels-Alder, but I'm just connecting it. This now looks like a benzene ring. Is this not a donating group? Is this not a withdrawing group? So what we're doing in this chapter can extrapolate to Diels-Alder chemistry as well. If you were struggling a little bit trying to identify donating and withdrawing groups, this chapter is surely going to help you on the Diels-Alder chapter. Because as you learn about donating and withdrawing groups on a benzene ring, you can look at your diene and your dienophile as parts. These are like segments of a benzene ring. And the groups off of those benzene ring segments can be considered either donating or withdrawing. So all of the same stuff, it's the same. It's not different for Diels-Alder than it is for benzene chemistry. I really want you to see that. Consider an alkyl group with an alkene at one end that does pi base chemistry. You have already done this where you've opened up the pi bond to form the more stable carbocation, and it was tertiary. Really, you've been doing what is effectively a segment, right, in our conjugated systems of a benzene ring. It's a part of a benzene ring, and a methyl group is considered to be an electron donating group by induction. You can draw it through its dipole. We've been doing that. You want more donating groups around stabilizing the carbocation. So all of the stuff that we've been doing is really the same. You have got the power and have had the power for a while now to look at a group off of a system and determine whether it's donating or withdrawing. So nothing has really changed. We're more formalizing it here, and we're going to rank things very soon. So what effect does having this donating group have on the incoming group, the directing effect? So this is what we're going to focus on now. I'm going to put rate aside. We've already done that, right? We know we can now look at two reactions and go, oh, that one will happen faster because it has a donating group versus the withdrawing group. You don't have to know what the products are to determine rate. Directing groups, though, is us determining what the product mixture might look like. So how can we do this? Well, you first have to look at the substituents already on the ring. And I've already got one. It's an amine group. And we've determined it's an electron donating group. We now have to decide which one of these, 1, 2, 3, or a combination, are going to be the major product mixtures for this system. Okay, here's what we need to know. We have our donating group, electron donating group. And what I'm going to draw your attention to down here is that the activators are listed on the left. So the strongest activators, the strongest ones, are the ones that when they're directly attached to the ring have a lone pair. See that? So they're directly attached to the benzene ring. Directly attached to the benzene ring, they have a lone pair they can donate. 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 So whenever you have an atom directly off of the benzene ring that has a lone pair, you can put it into the strong activator category. So those are kind of easy. You don't need to memorize these. A lone pair immediately adjacent to the ring, strong activator. Moderate activator. This is the torn atom. The atom directly off of the ring has a lone pair, but it could donate towards the ring. But it's also in resonance in the other direction, being pulled. It's kind of being pulled in two different directions. It still is a strong donator, but not as strong as, say, the OH, which only has one direction to donate towards. The oxygen that's torn between resonance in one direction and resonance in the other, it's got to split its time in a sense. So it's not as strong of a donator, but it's still pretty good. The weak donator is the one that's only a donator by induction, like CH3, any alkyl group, right? All the alkyl groups, they don't have a lone pair, but by induction, by a weak polarity, they are donating electron density just by sheer nature of being a tetrahedral cloud and sitting close to the benzene ring. It just kind of, by sitting there nearby, lends some electron density, electron cloud density. Okay, so from strong to weak, we know which ones activate, make the reaction faster. Weak deactivators, the ones that make the reaction slower. Well, these are all electron withdrawing groups, right? We already know that chlorine, bromine, iodine are electronegative, so they're very greedy and they pull electron density towards them. So they deactivate the ring. However, do they not have lone pairs? Yes, so they're the reluctant donor. But they're so electronegative, they deactivate. So they're just below an alkyl group, right? But they can't be placed as a strong activator because of their electronegative nature. All right, the next group we have are the carbonyls. Pretty much all of the carbonyls, like esters, aldehydes, ketones, they all have a strong dipole going to that carbonyl, and that's away from the benzene ring that it's attached to. So those are withdrawing groups. Same thing with these nitriles. The dipole is such that it's going away from the benzene ring. The following groups are very strong deactivators. Now, NO2, don't be fooled. Remember, a nitro group is an O-. The N is double bonded to an oxygen. The nitrogen is plus. We don't write the plus charge, but NO2 is an N plus O-. Overall, it's neutral. But take a look at that nitrogen. It's plus. It does not have a lone pair. The dipole for NO2 is most certainly going out and away from the benzene. So this is an extremely strong deactivator. This really slows a reaction down big time. In fact, some of the reactions that we studied, if a nitro group is on the benzene ring, sometimes they won't even occur because the nitro group just depowers the benzene ring as a nucleophile so much that the next reaction doesn't even work. If you have an ammonium system where the nitrogen has 3 groups like methyls off of it and has an overall positive charge, again, the nitrogen does not have a lone pair. It is not a donor. And lastly, a carbon with 3 halogens like CCl3, that's a very strong electron withdrawing group. That dipole is definitively out towards those chlorines and pulling electron density away from the benzene ring, stripping it of its nucleophilicity. Okay, so I just repeated myself on activators and deactivators. Get to the point, right? How am I going to decide which one of these products? Well, there is a trend, okay? What activates a ring as a donating group also helps the carbocation placement in that first step. I'm going to write out an exercise to show you that the major products for this particular reaction, when I do a bromination, is going to be para and ortho. Meta is not going to be seen. Why is that? Okay, so we've identified this as an electron donating group. Electron donating groups stabilize carbocations, right? We want carbocations to be around as many donating groups as possible. And remember, we're going to generate a carbocation in the first step of this reaction. So let's do an exercise to prove that ortho and para are the major products. All right, so I'm just going to do E+. Because what I want to tell you is that it does not matter what I use here. I could have nitrated. I could have sulfonated. I could have done a Friedel-Crafts. It doesn't matter. Whenever I start with an electron donating group on my ring, I'm going to favor para and ortho. It doesn't matter what the E+ is, and I'm going to prove that to you right now. Now, the first step, does it matter which double bond I use when I have a substituent on the ring? The answer is no. But I'm going to use the one on the left just to make it easier to follow along. There's my NH2. I didn't touch these other two double bonds. Where am I going to put the electrophile? Well, I'm going to put the electrophile at the ortho position to prove to you that the ortho is one of the major products. That means the carbocation left behind is right here. This spot is a very good spot to put the carbocation, because if you think about it, that carbon in blue, we want that carbon to be as close to the electron, the strong electron donating group as possible. Why? Because that donating group has a lone pair. It can resonate its electrons down and stabilize through resonance, added resonance. Okay, so that position's a really good position. Okay, where else could it go? What I'm going to do right now is I'm just going to show you that the position right at the foot of the electron donating group is a great position to be. Okay, so this proves ortho. Let's prove para. Okay, so I'm going to take my E plus and I'm going to attack the electrophile. Didn't touch this double bond, didn't touch this one. I'm going to put the electrophile para. That means the carbocation goes at this position. Now, by resonance, I'm going to show you that again, the carbocation is going to fall at that best position at the foot of the donating group. That carbocation fell right at the foot through resonance of the donating group. Okay, I could have maybe even started at the donating group and pushed the electrons in and over and out. I mean, that again also puts it at the para position. Either way you look at it, that carbocation will fall at the best, most stable possible position. Why? Because it has an extra resonance by the donating group's nitrogen, or you could just say it has strong inductive forces. It's tertiary, but it's stabilized by that electron donating nitrogen. Just to prove a point, I'm going to show you that putting the electrophile meta does no help in stabilizing the carbocation. So if I put the group meta, put that electrophile at the meta position, didn't touch these two. The electrophile's meta, the carbocation is at this ortho position. Try and try and try, you will never get the carbocation to be at the position that you want it to be, at the foot of the electron donating group. It just keeps bypassing it. So it's never going to be in a good position to be stabilized. So meta is not a good option for this reason. Ortho and para both can put the carbocation at the foot of the electron donating group, thus stabilizing the highly energetic intermediate and making things much better for the reaction to go. Okay, let's look at electron withdrawing groups. What you'll notice is that what is preferred is meta, and what is not observed are ortho, oops, I got them backwards, ortho and para. Okay? So we look at our benzene ring and we determine that the group off of it, due to the dipole, is a strong withdrawing group, or moderate withdrawing group, however we had it listed here. We had it in the moderate category. Okay, but it's a withdrawing group. Doesn't matter what I'm using. I could do any electrophile. It's always about the group that's already on the ring that directs the circus, right? This next group getting put on, I always think of it like siblings, right? Your firstborn was the ketone. Then the second child's coming onto the ring, and the first child's going to boss that second child and it's going to say, hey, you're going to go over here because I said so, right? So this directing effect is it's determined by who's already on the ring. It doesn't matter about like what you're putting on next. Boy, girl, electrophile, bromination, sulfonation, doesn't matter. The directing effect is all governed by the group that's already on the ring. And in this case, we have an electron withdrawing group. So electron withdrawing groups destabilize carbocations. Do you want a withdrawing group next to your empty carbocation? Withdrawing electrons that aren't there, right? It's empty. It's an empty orbital. You can't I can't withdraw money from an empty bank account. So withdrawing groups destabilize positive charges. So unlike the last case with donating groups, we wanted the carbocation to be right next to the donating group so I could make a donation towards it. It's empty. Here, have some electrons. Withdrawing groups, we would like to keep them away from the foot of the withdrawing group. So we've already kind of proven this in the last set of slides. If I place the incoming electrophile in the meta position, right? It's all about that first step. The carbocation goes ortho, the electrophile, the new incoming group, goes meta, and you can see that that positive charge is never going to be at the foot of the withdrawing group. By resonance, it is safe from ever being right next to the withdrawing group, which would be destabilizing. Right? That's the best we can do. We're not trying to, and that's why you'll never get a withdrawing group to be a good rate effector for these reactions. You're never going to have a good scenario where the withdrawing group suddenly stabilizes the carbocation. You're just trying to manage it. You're trying to do the best you can by just not placing them close to each other, right? It's like these two things have to be at a party together, but let's just try to keep them separated. So the best we can do is just to keep the carbocation away. And the way to do that is to put your electrophile at the meta position. Para or ortho, we can already prove to ourselves, again, we've already done this in the previous slides. If I introduce the electrophile at the para position, say, I can just do the para just to show you. The para position, here's the electrophile, didn't touch these double bonds. Carbocation goes here. Now, by resonance, oof, I end up really ending with the carbocation at the foot of the electron withdrawing group, which is not a good thing. Not a good thing. I was trying to avoid that, right? And this is bad. We want to avoid the ortho and the para because they put the carbocation directly at the foot of the withdrawing group. So here's my little trick here. If you determine that the withdrawing group, okay, the withdrawing group is off of the benzene ring and it's directing the incoming group, turn that W upside down and remind yourself that it goes meta. This is what I used to do when as an undergrad. When I was taking my exams, I'd be like, that's a withdrawing group. Withdrawing, and I'd make a W with my hand, and then I'd go, oh, W with your hand also is an M with your hand, right? You can just throw your hand down. Withdrawing, meta. Easy to remember. You don't have to work it out every single time, but you can rationalize it if you ever got stuck. So, up at the top, you can see activators and deactivators. This has to do with the rate. So when I ask you about rate, you know that the ones that are on the left are the activators, make things faster. The ones on the right make things slower. Okay? Now, look down at the bottom here. Ortho paradirectors and metadirectors. They have pretty much the same trend, but ooh, there's a little bit of a hiccup here. What you'll notice is that it's this silly halogen section that causes problems. On the one hand, halogens deactivate the ring. They're not really good at making the benzene ring a better nucleophile because they're so greedy and they're electron withdrawing. However, I told you they are the reluctant donors, right? They do have lone pairs. So when the reaction actually happens, let's say I had a chlorine and I introduced an electrophile. Again, doesn't matter what the incoming group is. It's all about who's already on the ring. This reaction would be sluggish. From a rate perspective, it would be sluggish. Why? Because chlorine's an electron withdrawing group and you're pulling electron density away from the ring. It's not a good nucleophile anymore. Okay, but from a directing group standpoint, when the electrophile gets attacked, the chlorine's like, fine, fine. I will help, that, oops, drew it from the wrong, using that double bond. Fine, fine, fine. I'll direct it ortho or para because by resonance, sure, I'll support the positive charge. I will reluctantly donate my lone pairs down if I must. Chlorine does have lone pairs, and if the carbocation happens to fall at my feet, I will be supportive of it. Okay, so it makes the reaction slow, but once the reaction is occurring, the chlorine is like, fine, I will be a donor for the sake of the carbocation. And so it actually becomes an OP director. Slows the reaction down, but reluctantly directs OP. So that's the reason. That's why halogens are sort of caught in the middle, right? But everything else behaves fine. NO2, being that it doesn't have lone pairs, is a really strong withdrawing group. You don't want the carbocation anywhere near it. And, far to the left, OHs and amines, they're great donating groups. All right, now let's kick it up a notch. What happens when the starting materials have two groups on the ring? Which one is going to direct the incoming sibling? Again, notice that I have the incoming group as E+, because it doesn't matter who's coming in. They have no say in the matter. They get put where they get told to be put. Who is going to be the boss? Well, it's not always the first child. And who knows which one went on first anyway, right? So what you got to do is you got to look at the ring and figure out who's the better activator. The stronger the activator, the more say in the matter they have. So what you do is you say, all right, this OH right here, how would you define it? Well, it's got lone pairs. It's an electron donating group. And this methyl group is also an electron donating group. But CH3 is a weaker donating group because it doesn't have a lone pair to give. So this is going to be my strong one. So I like to highlight my stronger one, my strongest electron donating group. That is the boss, okay? So that means that the electrophile, if it's a donating group, DO, O, leads you to the OP. Donating is OP, all right? So I'm going to highlight those OP positions. Relative to the boss, these are my ortho positions, and here is my para position. There's already something at the para position, so I can skip to the chase and tell you that the product for this reaction is going to place the electrophile at the ortho position. Okay, how about the next one? Who's the boss? Well, we have an electron donating group by induction. And NO2, oh yeah, that's the tricky one. Don't draw it out if you need to. This is a very strong electron withdrawing group. All right, so the boss is the donator. There's my boss. My boss is a donator, so donators do OP. So I'm going to look at the ortho positions relative to the boss and the para position relative to the boss. Oh, the para position's already taken up, so this one also goes ortho. NO2, CH3. Doesn't matter which side, it's a symmetrical system. Put the new incoming electrophile at the ortho position. Okay, how about the next one? Well, we've got two groups here. We've got an electron withdrawing group. This is electron withdrawing. And then this one, methyl, is an electron donating group. Whenever you have donating versus withdrawing, the donating group always wins. So this is the boss. And in this case, I've got OP relative to the boss because it's donating OP. There are the two ortho positions. Here's the para positions. All three are available to be substituted at. Which one is going to be the best? Well, it could be that we put it here, but if we put it here, then it's got steric hindrance on both sides. So that might not be the best thing. So we're going to start looking at steric hindrance effects. I've got two choices, and you probably will get a mixture of both. So I would say you would get a mixture of the para and the ortho. If I had to choose, I would probably pick the para only because being next to an sp2 carbon, which is flat and can get out of its way through rotation, might be a little easier than the CH3 right next door. But, you know, that's a tough call. How about this last one? We've got CN, which is C triple bond N, which is an electron withdrawing group. And we have NO2, which is one of the strongest electron withdrawing groups. So the one that's the lesser of the two evils, I wouldn't even call it, I'm just highlighting the boss. These are two very weak bosses, but the nitrile is weaker of a deactivator, right? Go back to the list. It's a deactivator, but it's not as bad as the ones far to the right. So because it has a dipole rather than an actual positive charge. So the boss, the reluctant boss, is this withdrawing group. Since we only have withdrawing groups, so we pick the not as bad withdrawing group as the boss. It's withdrawing, so it's going to direct meta. So let's see where that takes us. Meta or meta to the boss. Well, I'm going to pick the one that avoids as much steric hindrance as possible. So I would determine that the major product for this one, Cn and O2, would most likely be here. Whew, this is building and building, right? I'm going to leave you guys with some practice of your own. Here is a Friedel-Crafts alkylation, so you know how to put things on. You just have to pay attention to what's already on the ring and determine what the major product is. Choose only one major product and explain why you made this choice.